Alright, today we're looking at using machine learning to determine whether a machine is going to be broken, recovering, or normal at a certain point based on previous data. For pre-processing, I opened the data and dropped all of the rows with missing values and dropped the 15th column, or sensor 15's column, because it was all, like, the entire thing was missing data. I did this so it can keep the data clean. And then I put all of the data into test and training sets. With feature engineering, I found that there were 6 of these sensor readings that had the most importance. I used the importance feature selection graph to find these. The sensors were sensor 0, 0, sensor 0, 5, sensor 10, sensor 12, sensor 11, and sensor 51. These 3 had variations, like large variations between the means, but they were still had all the variables were like close to each other in their own column. I also used rolling statistics, which is basically when it moves along in the time series and recalculates the values based on the other data in the window specified. And this window I used was 5 data points. When exploring the data using the most critical values, I found that all of the important value features have a lot of variations. This shows that the data with high importance comes from different parts of the data set rather than features with very similar data. And another thing I found was that the number of recovering instances decreased significantly when you drop the missing data. And this shows that a lot of the time that the machine is recovering is, or could be, because of the missing data in these sensors. Now looking at the results, the random forest classifier has a high accuracy rating at 0.999664, so on, and a high F1 score, which is a mixture between the precision and recall, at 0.99964, which shows that this has a very, very high accuracy when trying to determine whether a instance belongs in broken, normal, or recovering classes. The other model that I used was the boosted random forest model, which is taking the normal algorithm of the random forest and adding an extra piece to the end where it gives more weight to the misclassified instances in each of the models and corrects the errors made by the previous models, which usually leads to a better score, which is why I chose this model, because I wanted to see if it would give me a higher score. But surprisingly, it gave me a worse score than the normal random forest algorithm. The last model I used is bagging using a decision tree as the weak learner, and as you can see, the accuracy is the lowest, and by lowest I mean by like 100th of a point lower, which shows that it's still a very good model, but it's not as good as the random forest by itself or the random forest boosted model. And how boosting or how bagging works is that the model uses a separate training subset that's created by the learner using bootstrap sampling, and then it averages the data and then puts it through a majority voting system, and that's how it classifies whether it's in the recovering, normal, or broken classification, which it would make sense why this would have a higher score, but it also kind of makes sense here where it would have a worse score, one being using a decision tree as the base, because decision trees are just all around worse learners than random forest is. But I tested it on random forest for bagging too, and it was worse than both the boosted and the normal one, which in this case I feel this is because the variance is too low. In conclusion, the best model was the random forest model with no boosting or bagging. One good thing about boosting and bagging is that it can help the performance of a lot of other data sets with the models, but this data set was one of those rare cases where the boosting and bagging did not help.